Hi! Matrices have a very robust interpretation as linear transformations by considering them as a standard matrix. If we consider linear transformations, it is hard to come up with something which cannot be expressed as a combination of rotation, reflection, and scaling. Indeed, in this lesson we will see that any matrix can be decomposed into exactly such a combination. The scaling component of this decomposition is given by the singular values of the matrix, and therefore it is called the singular value decomposition. Recall the notion of singular values of a matrix A, which are the square roots of the eigenvalues of the symmetric matrix A transpose times A. Recall, for instance, that if A is a 2 by 3 matrix, then the lowest singular value is 0, and the other two singular values correspond to the lengths of the semi-major and semi-minor axes of the ellipse obtained as the image of the unit sphere under the linear transformation with standard matrix A. One way to understand the transformation is by considering a particular choice of axes in R3, namely the one corresponding to the eigenvectors of A transpose times A, and then simply scaling by the singular values along these axes and embedding the result in R2 by matching the axes to their images under A. This loose description is formalized in the singular value decomposition. So let's put some of the relevant pieces in place. Let's consider the general case of an m by n matrix A of rank R. Recall that this rank is always smaller than or equal to the minimum of n and m. Then, since the matrix A transpose times A is symmetric, we know that it allows an orthonormal basis of eigenvectors for Rn. A choice of such an orthonormal basis of eigenvectors is called a set of right singular vectors of A. Note that the eigenvalue corresponding to the kth right singular vector is sigma k squared. So, for convenience, let's number these vectors to match the descending order of the singular values themselves, so that the vector v1 corresponds to the singular value sigma 1, the vector v2 corresponds to the sigma 2, and so on. Note that the matrix V, whose columns are the set of right singular values, is orthogonal, so V transpose is V inverse. Now, we note that the set obtained as the image of a set of right singular vectors is orthogonal by the direct computation of relevant dot products you can see on the slide. Moreover, since the lengths of these vectors are given exactly by the singular values, and we made sure to order them in line with the ordering of singular values, we see that the first R vectors are non-zero and the rest are zero by virtue of the rank of the matrix A. In particular, the set A times V1, A times V2, up to A times VR is an orthogonal basis of the column space of A. By normalizing this set, we obtain an orthonormal basis for the column space of A. We may then extend this basis for the subspace to a basis for the ambient space, Rm. In fact, we may extend it to an orthonormal basis for Rm. This is called a set of left singular vectors of A. Note that the matrix U, whose columns are a set of left singular vectors, is orthogonal, so U transpose is U inverse. In the loose description we saw earlier, the right singular vectors supply us with the axes in R3, and the left singular vectors supply us with the axes in R2. So the only thing left is to scale along the first axis by the corresponding singular value. For this, we consider the matrix sigma, which is very close to being diagonal. Indeed, we consider the R by R diagonal matrix D with the non-zero singular values on the diagonal, and then add rows or columns of zeros where necessary to obtain the n by m matrix sigma. Now, we note that when we normalized A times Vi to obtain Ui, this simply meant that we divided by the relevant singular values. So we find the expression for A times V seen on the slide. At the same time, however, we find obviously the same expression for U times sigma, which means we have obtained the decomposition of A as a product of three matrices, U, sigma, and V transpose. Note that here we use the fact that V is an orthogonal matrix, so V transpose is its inverse. What we just presented is actually a proof of the singular value decomposition theorem stated here on the slide. Take some time to read the statement. Note that the statement only refers to the existence, and indeed we made various choices that imply that the decomposition is not exactly unique. Although it is conventional to stick to the matrix sigma we have just found. In general, we call the columns of the matrix U left singular vectors and the columns of the matrix V right singular vectors. Consider the matrix A from before as an example. First of all, we consider the matrix A transpose times A and compute its eigenvalues to obtain the singular values and thus the matrix sigma. Note that the matrix A has rank 2, and so the third singular value is 0 and it does not appear in the matrix sigma. Of course, we'll also need the eigenvectors corresponding to these singular values, and indeed even orthonormalize this set of vectors to obtain the right singular vectors and thus the matrix V. Finally, we apply the matrix A to the right singular vectors and normalize the resulting set to obtain the left singular vectors and thus the matrix U. Finally, we see that indeed the product of U, sigma and V transpose is equal to the matrix A we started with. In conclusion, we see that we found quite a powerful result. Indeed, we have found an analog for diagonalization that works for any matrix A. The singular value decomposition knows many applications. Most of them center around the fact that it allows you to separate the effect of applying the matrix A into direction, where it scales up by a lot, scales up by a little, scales down, or scales down by a lot. Some notable applications include making the most reliable numerical approximations for solutions of linear systems, linear regression, and finding bases for fundamental subspaces. One very important application is found in the notion of principal component analysis. For more on this application, please have a look at the next lesson in this course.